This lesson is on exponent laws and roots and radicals. Generally, this is more of a review. If you want more detailed video lessons on each exponent law, I will link them throughout the video. But this lesson will cover negative exponents, zero exponents, exponents with numerical bases, rational exponents, looking at square roots and cube roots. First, I'm going to prove to you the negative exponent law, which you may have seen previously. When you are given two of the same bases and you are dividing them, there is a law for this. However, I'm going to show you what this actually means. X to the power of 5 is x multiplied by itself 5 times, and x to the power of 8 is x multiplied by itself 8 times. Showing it out like this, you can see that there are a lot of x's that get cancelled because one is on top of the other. And so what you're actually left with is 1 over x times x times x, which is the same thing as 1 times x to the 3. However, if we use the actual exponent law, where when you are dividing two of the same base, you subtract the exponents, you know that you would do x to the power of 5 minus 8, which gives you x to the negative 3. And although this is the correct answer, we use the negative exponent law to show that 1 over x to the 3 is the same thing as x to the negative 3. Therefore, the negative exponent rule is that x to the negative n equals 1 over x to the n, or also 1 over x to the negative n is equal to x to the n. Some examples: if I have a to the negative 5 and I want my exponent to be a positive exponent, I would just simply put it over 1 as in a fraction, and then I would change from a numerator to a denominator position to become 1 over a to the power of positive 5. Here I have a to the 3 times b to the negative 5. My 3 is positive, but my negative 5 is obviously negative. So I'm going to change where b to the negative 5 is and put it in the denominator position, but my a to the 3 is going to stay in the numerator position. Similarly, I have a to the negative 4, so I'm going to, again, change its position to the denominator for it to become 1 over a to the positive 4. If I'm giving something like 5a squared b to the negative 2, please remember that the 5 actually has an exponent on it. It is a 1, it is positive. So the 5 and the a squared, they stay in the numerator position, but we bring the b to the negative 2 to the denominator position, making it a positive exponent. In this example, I have a to the negative 3, b to the negative 2, and they are both negative exponents. Now, technically, they are all over 1 as a fraction, so I'm going to keep the 1 on the numerator position, and I'm going to move the a and the b to the denominator, and their exponents become positive in this way. And for my last example, I have a negative exponent on the top and a negative exponent on the bottom. So all I'm going to be doing is I'm actually going to be changing the position of both the x and the y, where now the y becomes a positive 3 exponent on the top, and the x becomes a positive 2 exponent on the bottom. Here is a really good practice problems for you. I encourage you to pause this video, and I will go over each solution on the next slide. For the first one, what a lot of people get mixed up about is the fact that the 2 is negative. Although the 2 is negative, it still has a positive 1 exponent, so we actually don't need to move it. It's the x and the y that we will need to move into the denominator for it to become positive, and this becomes the final answer. In the second example, both the x and the y have negative 5s as exponents, so I'm going to change both of them to go into the denominator position to become a positive 5 exponent. In this next example, I have an actual negative exponent on my numerical base, which is a 2. So I'm going to move that to the denominator position, which would become 2 to the power of 2, which is just 4. And I leave my x in the numerator position because it already has a positive 2 exponent. In this fourth example, I have a lot of negative exponents. So I'm actually just going to switch everything. So the x to the negative 2 and the y to the negative 3 will go to the denominator, and the x to the negative 3 and the y to the negative 4 are going to go to the top. Or you could just subtract also your exponents here on the x's and subtract your exponents here on the y. You would do negative 2 minus negative 3, which is negative 2 plus 3. And then you do negative 3 minus negative 4, which is negative 3 plus 4. In the end, the answer is just a simple xy. For question 5, you would have to remember to bring your negative 2 inside the brackets, or if you wanted to, you could actually put all of this over 1, and then this would become a positive 2, and you could then multiply them inside. Regardless, the answer is going to be 1 over a 4 because we have 2 to the power of 2. 4 times x to the 6 times y to the 4. For question 6, you have a negative exponent here on the x to the negative 3. So you would bring that to the denominator position under the 2x squared. And then you would subtract your exponents. Or here you could just also add the exponents. There's really several ways that you could do this. But in the end, if you added your exponents on the top, you would get x to the negative 1. If you brought your x to the negative 3 on the bottom and then you subtracted them, you would still get x in the denominator position for it to be a positive exponent. And in my last example here, I have a negative 2 divided by a negative 4. So I'm going to put the 2 on the bottom here because it is 1/2. And then I can also just subtract my exponents here, subtract my exponents here. But regardless, they would become a negative exponent on the top, so I would have to bring them to the bottom. The answer is 1 over 2a to the 3b to the 4. Next, we're going to talk about the zero exponent rule. So if you remember something like this, where you would subtract your exponents, you would get x to the 0. But at the same time, you should also know that something divided by itself is also 1. So in this case, it's kind of like we're given the same thing. Here's another example. So I have 2 minus 2 gives me 0, x to the 0. But then I also know that anything divided by itself is 1. And my last example, x to the 4 over x to the 4, you minus your exponents, you get 0. But you also know that when you divide two of the same things, you get it equal to 1. So the rule is that x to the power of 0 is also equal to 1, provided that x does not equal to 0. Here are some examples for you to practice, so I encourage you to pause this video if you would like to check your answers. I will go and speak about the solutions on the next slide. So for the first one, even though you see a negative in front of your x, because it is in brackets, it's basically saying that that whole thing is to the power of 0, so your answer is just 1. For the second one, it's exactly the same thing as the first one. Because it's in brackets, everything is to the power of 0, so I just know that it is equal to 1. However, for the third one, I do have a negative on the outside of my brackets. So while everything on my inside is equal to 1, I do need to remember to hook that negative on top of the 1 in front, so it becomes negative 1. For this one, it's the same thing, whereas everything on the inside is the power of 0. So although you see the negative right in front of the 5 here, this whole thing is in brackets to the power of 0, so it's 1. But then you have to remember to bring this negative in front at the end. Over here, you have everything here in the brackets is equal to 1, but there's a negative in front, so it becomes negative 1. And then on the bottom in the denominator, we have this is 1, and 0 to the power of 1 is just 0. So in the end, I actually have negative 1 divided by 1, which is just equal to negative 1. For question 6, you have 5 times x to the 0, which is just 5 times 1, so the answer is 5. For question 7, you have a negative 5 to the 0, so this becomes negative 1. And then everything in brackets here is to the power of 0, so it's also 1. So now I have negative 1 times 1, which is just negative 1. For question 8, you kind of have to go term by term here. 5 is 5, x to the 0 is 1, so I don't have to put it, and then I have a y squared. Minus, this is in brackets to the power of 0, so it's just equal to 1. Plus 5y squared. So in here, I'm just going to add my like terms, which are 5y squared plus 5y squared. So my final answer is going to be 10y squared plus 1.
For my next example, going again turn by turn, I have 5 times x to the 0, which is just 5 times 1, which is 5, minus 5 to x to the power of 0, which is 1, so minus 1. Plus, again, this is to the power of 0, so it's 1. So I have 5 minus 1 plus 1, which is equal to 5. And then in my last example here, I need you to know that when you have negative x to the power of 4, it's the same thing as doing negative x times negative x times negative x times negative x, which actually becomes the same thing as positive x to the 4. So I just rewrote it as a positive x to the 4. Same thing on the bottom, I rewrote this as a positive x to the 4, but I added the minus on the inside. So now I have x to the 4 over negative x to the 4 in the first fraction. In the second fraction, I have x to the power of 0, which is 1 over 2. So in this case, this becomes negative 1. So I'm going to do negative 1 minus a half, which is just negative 1/2.
Next, we're going to go over exponents with bases that are numbers. We call this numerical bases. And before we go over any examples, you're going to need to recall the exponent laws that you would have seen using variables, meaning x, y, any letter. So for the first one, the multiplication of identical variables, when you multiply two variables that are the same, you keep the variable and you add the exponents. When you divide variables that are identical, you keep the variable and you subtract the exponents. And when you do the power of a power of identical variables, this looks like when you have an exponent on the inside of a bracket and the exponent on the outside of a bracket, you keep the variable and you multiply the exponents. Keeping these rules in mind is the same thing as if you had bases that are numbers instead of letters. So here's my first example. I have two of the same base, the base 2 and the base 2. One is to the power of 5, one is to the power of 2. You keep the base, you add the exponents. And to prove this to you, 2 to the power of 5 expanded looks like this, and 2 to the power of 2 expanded looks like this, and in total I have 7 2's. So you keep the base and you add the exponents. For my second example, if you have two of the same base here that are being divided, so I have 2 to the power of 5 over 2 to the power of 2. What a lot of people tend to do is they tend to make this equal to 1 to the power of 3, and that's incorrect. You keep the base and you subtract the exponents. 5 minus 2 is 3. And just to prove it to you, I expanded it out for you here. 2 to the power of 5 looks like this. 2 to the power of 2 looks like this. And if you cross off the 2's that you can, you are left with 3 2's or 2 to the power of 3. So again, you keep the base and you subtract the exponents. And in my power of a power example, I have 2 to the power of 3 to the power of 2 to the power of 3. So I'm going to multiply the 2 and the 3. I'm going to keep the 2. I'm going to get 2 to the power of 6. To prove it to you, 2 to the power of 2 3 times looks like this. And if I add the number of 2's that I see, it gives me 2 to the power of 6. So once again, you're keeping your base and you're multiplying your exponents. What happens though if you have a lot of different bases? Well, it would be a really great idea for you to identify bases that are able to be changed to an exponent law. So this is what I mean by that. If I have 2 to the power of 2 times 4 to the power of 2 times 8 to the power of 2, you'll realize that I have 3 different bases. I would aim to get everything looking like my smallest base, which in this case is a 2. Now, luckily I can. I know that 4 to the power of 2 is also known as 2 to the power of 2. And I also know that 8 is equal to 2 to the power of 3. To the power of 2, of course, on the outside, same with my 4 to the power of 2. And then what happens here is I do my power of a power law, 2 to the power of 2 times 2 to the power of 4 times 2 to the power of 6, and then I do my multiplication law where I'm going to add my exponents. And I get that this, what looked a little bit complicated, just becomes 2 to the power of 12. Another example here is if I have 2 to the power of 6 over 4 to the power of 2. My smallest base is that of a 2. So I'm going to see if I can change my 4 to have a base of 2 as well, and I can. So I now have 2 to the power of 2 on the top and 2 to the power of 2 times 2 to the power of 2, to the power of 2 on the bottom. When I do my power of a power law, I get 2 to the power of 4 on the bottom, and then if I do my division law, where I subtract my exponents, I get 2 to the power of 2, which is just 4. Now, of course, I know that if you're given something like this or even something like this, originally you can technically use a calculator, but just because we are doing things with exponents and exponent laws, just be careful. Sometimes it's actually easier or it's being asked that you keep it as an exponent and not as a whole number. Here are 4 questions for you that you can use to practice. I encourage you to pause this video, but I will go over the solutions on the next slide. For the first question, I have a base of 3 and a base of 27, but 3 is my lowest base. So my goal is to see if I can make my 27 become a base of 3, and of course it can. So I have 3 to the power of 2 times 3 to the power of 3 to the power of 2. Doing my power of power law, I get 3 to the power of 2 times 3 to the power of 6, which equals to 3 to the power of 8 after I add my exponents. In my second example, I have a 3 to the base on top and I have a 9 base on the bottom, but I can change my 9 base to a 3 base because I know that 9 is equal to 3 to the power of 2. So now I have 3 to the power of 2 to the power of 2. If I multiply my exponents, I get 3 to the power of 4, and then if I subtract my exponents, I get a good old 3. For my third example, I have a lot of bases, but I know that I'm aiming to get my base into a base 5. 25 becomes 5 to the power of 2, and 125 becomes 5 to the power of 3. In the middle here, though, I have to remember that I have to do my power of a power law to get 2 times 3, which is 6. And then once I add my exponents together, I get 5 to the power of 11. In my last example, I have a base of 2, 16, and 4. So I'm going to aim to change all of my bases that are not 2 to 2. So in the first one, I'm going to leave 2 to the 2 here, but 16 is also known as 2 to the power of 4. So I've just replaced my 16 with 2 to the power of 4, bringing my 2 on the outside because I can't forget that. And then I changed my 4 here to 2 to the power of 2 with the 3 on the outside. Same thing on the bottom. Doing my power to a power law, I get 2 to the power of 2 times 2 to the power of 8, because 4 times 2 is 8, times 2 to the power of 6, because 2 times 3 is 6, and on the bottom, 2 to the power of 4, because 2 times 2 is 4. Once I add my exponents on the top, I get 2 to the power of 16, and then I'm going to subtract because I am dividing, and I get 2 to the power of 12 as my final answer. Let's move on and talk about square roots for a second. First, you should know that every positive number has a positive and a negative square root. So for example, or every positive number that has a square root has a positive and negative square root. For example, 36 is the same thing as 6 times 6, but it's also the same thing as negative 6 times negative 6. This is very important for you to know this, especially when you are going to do more complicated algebra with variables. When the symbol, this is the radical symbol that we use, only the positive or the principal square root is considered. So we do often say that the square root of 36 is equal to 6, but it's not wrong to say that it is equal to negative 6 as well. Now if we talk about rational exponents and square roots, the first thing that you might already know, especially when you're solving an equation, is the square root of a to the power of 2 is equal to a. It's kind of like you think of this as the 2 on the outside cancels the radical symbol here, and then you're just left with a. However, there is something deeper that you need to know. The square root of a is actually also known as 1/2 as an exponent. This is called a rational exponent. And when you have something like a to the 1/2 to the power of 2, if you do your power of a power law, you multiply half by 2 and you get a to the power of 1, which is equal to a. So we come up with this rule as a to the 1/2 is equal to the square root of a. And knowing that, if you take the square root of a and you square it, you get just a to the power of 1. Here are some examples where you should know how to square root certain numbers, but also how to square root certain variables with exponents. You can pause this video, try these examples, and I will go over the solutions on the next slide. For the first one, you're just rooting both the top and the bottom. So we're going to do the root of 4 and the root of 225, and we're just going to get a nice 2 over 15. For the next one, if you remember what I said in 2 slides ago, when you have a square root and a square, they cancel each other out. So you are left with 8 over 9. Again, also the root here is also known as to the power of 1/2. And so this just becomes 2 times 1/2, 2 times 1/2. You're still left with 8 over 9. In my third example, you just have to square root 100 and square root 25. In the end, you get 10 over 5, which is equal to 2. In this example, you are basically just going to root every term. So you're going to root 0.04, you're going to root x to the negative 2, and you're going to root y to the negative 4. Doing that with the first one, you're just going to get 0.2. However, when you are square rooting a negative 2, you are going to get a negative 1, because this is again also equal to the power of 1/2. So I had to bring my x to the bottom to make it a positive 1. Also, if I go to my y to the 4, if I root y to the 4, it's the same thing as doing y to the negative 4 times 1/2. And half of 4 is 2, but in this case it's a negative 2, so I do have to bring it to the bottom for it to become a positive 2. In my last example, do not ignore this negative. It is very important, but you are going to root everything on the inside. So first, when you root the 169, you do get 13 with a negative here in front. Then over here, you would divide everything by 2, or you would times everything by 1/2 because it is rooted. So if I would do negative 10 times 1/2, or negative 10 divided by 2, I get a negative 5, so it needs to go downstairs to become positive. My 22 divided by 2 or times 1/2 becomes 11, which stays on the top because it's already positive. And my z to the negative 16 times 1/2 or negative 16 divided by 2 gives me a negative 8. So I do have to bring it to the bottom for it to become a positive 8. Let's talk about rational exponents and cube roots. So cube roots is when you have something that is rooted by the 3. So it's kind of the same thing as square roots, except we're dealing with the number 3 instead of the number 2. But you may have known from solving some equations that if you were to cube a cube root, it's kind of like they cancel each other out and you're left with b. This is because the cube root of b is also known as b to the 1/3. And if you do 1/3 times 3, power of a power law, you get b to the 1, which is just b. That is why we say that it cancels each other out. Another way of saying it is that you do need to remember that b to the 1/3 is equal to the cube root of b. And knowing that, it just kind of means that when you are dealing with a cube root, you can multiply everything inside the root by 1/3 to make your exponents smaller. So in this case, if I have the cube root of a to the power of 3, it equals to a because a times a times a is equal to a to the 3. And in this case, the cube root of 8 is equal to 2, since 2 times 2 times 2 is equal to 2 to the power of 3, which is equal to 8. So therefore, if I do the cube root of -8, it should be equal to 2 because I do -2 times -2 times -2, which is also known as -2 to the power of 3, which is equal to -8. Here are some examples for you to practice on your own. I encourage you to pause this video, but I will go over the answers on the next slide. So for the first one, you would just have to cube a -27. What times itself 3 times will give you -27? The answer is -3. For the second example, if I were to cube root every term in here, let's start with the -64. If I were to cube root the -64, a number that multiplied by itself 3 times gives me -64 is -4. But then if I look at my variables, remember when you have exponents, the cube root is also known as to the power of 1/3. So you're basically doing 3 times 1/3 or 3 divided by 3. In the end, you're just left with an exponent of 1 on both the a and the b. In my third example, I'm going to cube root the -0.125 to give me -0.5. And I'm going to multiply my exponents on my variables by 1/3 or divide by 3. It's the same thing. So I get x to the 5 when I divide this by 3, it stays on the top. Y to the 0 is equal to 1, so it just kind of goes away. And my -24 on the z is either going to be multiplied by 1/3 or divided by 3. But I do get a -8 on the top, so I do need to bring it to the bottom, so it becomes z to the 8. In my fourth example, this is basically just saying that you actually need to cube root every single thing inside the root, including the denominator. By doing that, on my exponents and my variables, I'm going to multiply them by 1/3, so I get x to the 1, y to the 4, z to the 2, and on the bottom, the cube root of 216 is just 6. In my last example here, I do have a square on the outside, but I do need to deal with my cube root on the inside first. And so what's going to happen here is I'm going to cube 64, which is actually going to give me 4. I'm going to cube the a, the b, and the c, which is actually just going to give me a, b, and c. But then when I bring my 2 here on the outside in, I'm going to have 4 to the power of 2, which is 16, a to the power of 1 times 2, which is 2, b to the power of 1 times 2, which is 2, and c to the power of 1 times 2, which is 2. If we look at some more rules in detail for radical exponents, as I mentioned at the beginning of this video, I do have a more specific video lesson on just radical exponents that I'll link here so that you can check it out. But generally, the rule is that anything to the power of 1 over n is equal to that n's root, the nth root of a. So this is kind of what I mean by a rational exponent as well, as when the exponent is a fraction. Now you don't need to worry because a lot of this stuff here is also just dealing with power of power laws. However, it's a good thing for you to know what a half or any kind of radical means when you want to change it into a exponent. So in this case, I encourage you to pause this video, try these out, and go on to the next slide for the answers. So for the first one, 16 to the 1/2 is just the square root of 16, which is 4. For this one, you do have to multiply your 1/3 inside. You can also say to yourself that you are cube rooting all of the exponents or cube rooting all of your variables. But in the end, you get x to the 5. Your y becomes a -7, so you have to put it on the bottom. And your z becomes a -1 on the bottom, so you have to bring it to the top. This is also just saying the cube root of -64, which is -4. Here we have a lot going on. So term by term, we have the square root of 9, which is 3. We have the 4th root of 16, which is 2, but there's a negative in front of it. We also have the 4th root of 81, which is 3. And then we have a -3 times 3 to the -2, which in this case, you bring your 3 to the bottom. So you get 3 over 3 to the 2, which is -1 over 3. If you add all of these up, you just get 3 2/3. For the last one, again, term by term, you are going to cube root the 8 on the bottom, and then you'd get 1 over 2. Minus, you're going to cube root your 27 and your 125 to get -3 over 5. In this case, this is the fourth root of 16 times 2. The fourth root of 16 is 2, and then you're going to multiply it by 2, which is 4. And then here, anything to the power of 0 is 1, so you're going to just do minus 1. If you add all of these together, you get the answer 2 and 9/10. The second rule is just if you have something like a to the power of m over n, it is the same thing as a to the power of 1 over m with the m on the outside. This might be helpful because sometimes you might see a fraction and you're not sure how to manage that fraction. So it might help for you to just kind of take the numerator out of the equation and have it into some kind of just 1 over a number and then do the root of that number. So here's an example. I have 4 to the 3 over 2, which is the same thing as 4 to the 1/2 times 3. And I know that 4 to the 1/2 is the same thing as the square root of 4, which is 2. So in the end, I get 2 to the power of 3, which is 8. Here's my other example. I'm going to bring the 3 on the outside, keep my 1/2 on the 9, and then I'm going to do the square root of 9, which is 3 to the power of 3, which is 27. Here, I remove my 3 to the outside. I do the fourth root of 16, which is 2, to the power of 3, which was on the outside, which gives me 8. In this case, dealing with a negative exponent, you need to remember to change its position to the denominator to make it positive, which is what I did here. Then I removed my 3 on the outside. I square rooted because it's to the power of 1/2, 121, which gives me 11. And then I do 11 to the power of 3, which is 1,331. For this one, I decided that I was going to multiply my fractions on the outside in, and I get 16 to the negative 1/4. However, it's a negative. I do have to bring it downstairs first, and then I'm going to square root or fourth root it, to give me 1 over 2. In this example, I'm going to take my 3 and bring it on the outside, but I did want to show you that it does become 81 to the 1/4, which is known as the fourth root of 81. In this case, the fourth root of 81 is 3. 3 to the power of 3 is 27. Here, I also wanted to show you that there's another rule that you might have seen before when it comes to radicals, where instead of taking the 2 and putting it on the outside, you can just bring the 5 and radical the 5 here. So in this case, this is the fifth root of negative 32 to the power of 2. The fifth root of negative 32 is negative 2, and negative 2 to the power of 2 is a positive 4. Here are some more examples for you to practice on your own. I encourage you to pause this video, try them, and then press play to see the solutions. In this case, 125 to the power of 2 over 3 is the same thing as saying the cube root of 125 to the power of 2. The cube root of 125 is 5 to the power of 2 is 25. In this case, I would do 1 over 64 to the power of 5 over 6 to make it positive. I would bring my 5 on the outside. I would sixth root my 64 to the power of 5. That gives me 32. Over here, I have the square root of 9, which is 3. And in this case, I have the square root of 9, which is 3 to the power of 3, which is 27. So I have 3 times 27, which gives me 81. In this case, I would do 1 over all of this stuff to the power of a positive 3 over 2. I would bring my 3 on the outside, and then I would divide everything on the inside by 2 before bringing my 3 back on the inside. So you get 1 over a to the 9, b to the 15, 6 to c to the 18. Over here, if I go term by term, the square root of 81 is 9. The cube root of 8 is 2. Negative 32 to the 3 over 5 is the same thing as the fifth root of 32 to the power of 3, which is negative 8. And this here, you do have to put 1 over 32 to the power of 1 over 5, which is also known as the fifth root of 32, which is 2. Adding all of these together, I get 3 1/2. Finally, to go over everything we covered in this video lesson, we went over the negative exponent rule, how to make exponents that are negative positive. We went over the zero exponent rule, where anything to the power of 0 is equal to 1. We went over the fact that exponents with numerical identical bases is the same thing as exponents with identical variable bases. When you multiply, you keep the base and add the exponents. When you divide, you keep the base and you subtract the exponents. When you do power of a power, you keep the base and you multiply the exponents. And finally, we just went over rational exponents and radicals and roots, where for square roots, you know that a to the 1/2 is the same thing as the square root of a and vice versa. For cube roots, b to the power of 1/3 is the cube root of b and vice versa. And don't forget these two other rules that might help you when you are solving complicated algebraic expressions, where you can just say a to the power of 1 over n is the nth root of that letter or that number. And a to the m over n, you can just make it so that the m goes on the outside and you have an a to the 1 over n, which brings you back to rule number 1. Thanks for watching.